All right. Welcome to all of you here. You know why you're here, and the program explains it all very well, but welcome to our annual Lindbergh-King Lecture. I think one of the most interesting and finest things we do every year. I think this is going to be particularly... You're not hearing too well. Let's try this one. Welcome again to everybody. All right. You all have a program, you're all literate, and you know why you're here. But I think I just want to welcome you to the annual Lindbergh-King Lecture. It's one of the exciting events that we put on. We all look forward to it. Particularly, we're looking forward to today's talk. I would like to present Dr. Brennan, who will set the stage for this, and also introduce Dr. Feigenbaum, our speaker for today. Patty?
Good afternoon and welcome to the National Library of Medicine. I am very delighted to present the opening remarks this afternoon, to welcome you to this lecture that we have in honor of these two great men who sadly we've lost since the last time we had the Lindbergh-King Lecture. I'm very thrilled to let you know that Mary Lindbergh is here in the front with us today to represent the tradition and to enjoy the fellowship that this lecture is bringing about. Who would have thought that two physicians, pathologists, crossing paths at Columbia University years ago would have transformed medical informatics? The loss of these two physicians is great, and yet their legacy is even greater, so we are proud to stand on the shoulders. We must remember, as we listen to and think about what Drs. King and Lindbergh brought us, many advances, many important and inspirational strategies for new knowledge. They also brought us whimsy and humor. Who would have thought of naming one of the most important innovations for clinical practice, Grateful Med, and sending it out to the world for $29.95 a shot? Who but Dr. King could have brought us the graciousness, his ambassadorship for the National Library of Medicine, his advocacy, and his service to us was tremendous. They would have both been proud to be here today. Maybe a little puzzled, as we all have looked at the AI events over the last 30 to 40 years and wondered, where are they going? I think we're going to hear some exciting ideas today about where they are going. It's particularly important, though, at the NIH right now that we take a moment to pause and learn from this great thinker, Dr. Ed Feigenbaum, about artificial intelligence, its past, its currency, and its future. NIH and the National Library of Medicine in particular are beginning to understand how to best stimulate new algorithms, new uses of AI, because we have the data and the compute power that we've never had before. We're looking at artificial intelligence as a way to both revolutionize biomedical discovery, to enhance and accelerate clinical practice decision-making, and even to make the NIH's operations run better. Even today, as you're all sitting here, there's a machine learning algorithm running upstairs, or maybe downstairs, I guess, making sure that our PubMed citations are now presented in a relevance-based ranking, getting them into the hands of individuals more quickly. That machine learning algorithm, developed by Jian Liu and his team, allows for understanding of what the query is from the individual and effective matching of those millions of articles to the right set. This is important because, as you all know, when you launch a PubMed search, you touch our vast resources, but when you actually review your citations, you often don't go past the first page. So if we can get the right citations on the right first page, we're in luck. Across the NIH, artificial intelligence, particularly natural language processing and machine learning algorithms, are being used to enhance operations. Led by a team at the National Institute of General Medical Sciences, programs have been developed that assure effective matching of research proposals to reviewers. Now, you may not all realize, but NIH gets 80,000 proposals a year and has to assign them to 40,000 reviewers. The combinatorics are phenomenal. It takes weeks to make these assignments. Yet, envisioned by and implemented through a natural language processing program, the team has found a way to actually shorten that cycle of assignment from several weeks to several days, and allows the program officers to be able to apply human logic when human logic is most essential. So we have a bright future, we believe, for artificial intelligence, but don't put your blankets away because the winter might come back again before the next phase comes. Nonetheless, I'm confident that with the tools we have and the reasonable, rational, and visionary thinking that the NIH and particularly the National Library of Medicine has, we could make this future great. We'll be inspired today by the words of Dr. Edward Feigenbaum. He's a professor emeritus from Stanford University, well known to many of us who've been reading his works for years and inspired by them. Known as the father of expert systems, we just chatted about where did this artificial intelligence word comes from. And he has embedded in his soul the history of the emergence of the idea that a system could, in fact, lead to better choices, better understanding, better decisions, whether or not it actually operated exactly as a human did. He defines himself as a systems analyst, and as an industrial engineer, I find that phrasing very important. And as a pioneer, he developed and founded the KSL, the Knowledge Systems Laboratory at Stanford, and has demonstrated both in industry as well as in academia the importance of artificial intelligence. He identified that AI has had two waves already, and we're maybe getting ready for the third. The first produced many models of computer expertise, behaving at human levels of performance, maybe a little bit beyond, but in very narrow areas of human and professional work. Presently, we focus on perception and deep learning, but he envisions a future where creativity and creative behavior well beyond human capacity might be enabled using deep thinking. I invite you to join with me to welcome Dr. Feigenbaum and enjoy the next set of remarks. Thank you for being here with us.
I want to make sure to get the right microphone. Is this one working? They both work. Yes, Patty, I think I'll mention that in my remembering Don Lindbergh, that he wouldn't be surprised by any of what I'm going to say. In fact, Don and I, if you see in the last line there, we talked about the topic for this talk, and one of the options I offered him was the one that you mentioned, the past, present, and future. He said, "Oh no, anybody can give that talk. Don't do that." So that's this talk on AI and creativity was the result of Don's choice of that. So I'm not going to be, although I decided to sneak in a slide about the past, present, and future. But when you, of course, we will all miss Don terribly, but when you read what the director of NIH wrote in his tribute to Don, he didn't talk about what Don knew about AI. I met Don Lindbergh on the first study section ever here at NIH that included computing and computer science. Now some of the people on that study section are legends in computing and computer science, like Oliver Selfridge and Alan Newell and Don. And then when we formed a national organization called AIM, Artificial Intelligence in Medicine, when the internet hadn't been invented yet, but the ARPANET was gluing some of us together, a small number of us. And we made sure that the small number included anyone interested in AI and medicine, and ARPA agreed to that. And so with Stanford as being the hub of that community, Don agreed to be our first chairman, and he did a great job in welding together that community. At the same time, he was doing an expert system in a collaboration with Rutgers, and the IEEE paper, and he published several papers on it, but the IEEE paper on it, on AI Room, Don was the first author on that paper, and he really understood the innards of AI. But he was absolutely a visionary with regard to the AI science. That is, he wasn't looking at next year or next decade. He was looking at 30, 50 years out. What kind of research should be sponsored both here in the Lister Hill Center and with extramural funds. And then, of course, the bioinformatics opportunity came along, and Don said, yes, that's it. Libraries need to do that. And then he supported that. And then, of course, he would always talk about the future, the libraries of the future. In fact, I chaired a panel at the Computer History Museum once on that topic, and Don came out and participated in that. Okay, onward. I want to begin by just giving you a few words that I'll be using continually in this talk. Keyword, behavioral. This is going to be a behavioral view of what is creativity, and I'll tell you about that in detail. I want you to keep in mind the idea of a search space. That is, when we're doing problem solving of any kind, what we're doing is exploring a vast, gigantic maze of possibilities, of possible subproblems and how they break down and what to attend to and what not to attend to. I'll tell you the details about that. That vast search is controlled by heuristics. Heuristics allow you to prune that search to reasonable levels that can be accomplished in times relevant to humans. And then I'll apply that to all these ideas to creativity. Okay, what's the prehistory of this? Well, you all know Alan Turing. Those of you who don't know him as a logician, at least you may have seen the movie, The Imitation Game. He was the famous code breaker for the Enigma code, one of the greatest logicians of the 20th century, and also regarded as the father of computer science. But he wrote two key papers, one in 1949, internal to the British government, and one external in a journal called Mind, on the nature of intelligence and whether machines could do that. And he came up with that game that is called the imitation game, but it really means that a computer could be regarded as intelligent when its behavior is indistinguishable from that of people. So his focus was on behavior. This was a tremendous leap forward, actually, in changing of mindset. What he was really saying was, evidence counts. Reminds me of medicine. Evidence-based behavior. It's what the behavior is as evidence, not your preordained condition, not your ideal condition, not whatever you think, whether you're religious or philosophical or doesn't matter. Look at the evidence. Look at the evidence when the behavior is indistinguishable from that of people. Okay, now what do I mean? So now I have to take a behavioral view. Where is that green pointer here? Now I have to take a behavioral view of creative. What do I really mean by creative? Well, something is, a creative act means, for me, these three things. It's extremely surprising to those who are expert in the field. It's novel, and may even be so novel that it's new to mankind. It could be novel in the context of a particular problem, but sometimes the particular behavioral act or idea that comes out is never been seen before by people. And the third thing is that it evokes awe in the community, in these community viewing this, particularly the community of specialists in the particular area. And I kind of paraphrase that as, wow, how did he or she think of that? Fantastic. So I'll give you some examples of that. This is a highly empirical view following what Alan Turing taught us. And what I won't be talking about, of course, there are many other modes of creativity than the one I'm going to be describing. I'm going to be describing combinatorial creativity, but there are other ways to be creative. And I'm not going to talk about the what I call the Everests of human thought. So I'm not going to say what Einstein did when he was inventing the special and general theories of relativity, or Newton, or Mozart, or Beethoven, or Picasso. I'm not going to be talking about that. That's just a different ballpark. Now, this idea of modeling creativity using information processes goes back, actually, 60 years. 1959, the first paper, The Processes of Creative Thinking, by Alan Newell and Cliff Shaw, who was a programmer at the Rand Corporation, and Herbert Simon. Newell and Simon are two of the four founders of AI. Shaw was a brilliant programmer at the Rand Corporation. This happens to be a Rand Corporation document. The view taken there is, and I'm quoting them, creative thinking is simply a special kind of problem-solving behavior that is characterized by the novelty and difficulty of the task. So they don't include some of my things like awe, but that's their characterization. And it came very early in the history of AI. If you think of the history of AI as beginning in early 1956, and the first AI conference in the summer of 1956, this first draft of this paper was written in 1958. So that's remarkable. But we have a lot of perspective on this. You know, we're 60 years into this now. So from history, we can tease out examples of what Newell and Simon were talking about. Incidentally, Herb Simon, maybe you all know, but he's one of our guys. It's computer science, AI, but he won the Nobel Prize in economics, and Alan Newell won the National Medal of Science. Both of them won the highest awards you can win in computer science and psychology, both. So these are tremendous minds that were working on this problem. Okay, now this is where Patty, this is where I'm sneaking in okay, so artificial intelligence. Well, the first thing you can do is to drop the artificial, because this is just what intelligence is all about. Intelligence, I divide into two things. Whoops. Is this working? Yeah. Recognition, which is otherwise known in psychology as perception, and cognition, which is otherwise known as thinking. So this is the classification and identification of objects, and on the thinking side, we have words like planning, problem solving, abstraction, and of course creating. So here's a spectrum. You hear a lot these days about situation understanding, both visual and using other wavelengths other than the visual wavelength. You can use radar or infrared or other or sound sensing. And so you hear a lot about this in connection with medical equipment or self-driving cars, or these are all sensations that are processed. Natural language understanding used to be the game of the linguists, but now it's sort of shared game with the statisticians in terms of counting the number of usages of a word, the number of paired usages, the number of various combinations of usages. But in order to achieve anything from the processing leading to understanding, you're going to need something else. And the something else is semantic knowledge, knowledge of the world, whether it's expert knowledge or whether it's common sense knowledge. There are many different, very large knowledge bases that inform that kind of understanding. I mentioned some of them here. WordNet, started by George Miller at Harvard and Princeton, now has about 800,000 nodes. And then there's word triples, and Freebase was bought by Google. It's been expanded to have now millions of things in it. And ConceptNet is like WordNet except for concepts, not words. In order to understand natural language, whether it's statistical or whether it's based on linguistic rules, you still have to consult the semantics, because words without the semantics are meaningless, and statistics of words without the semantics don't mean anything. So again, you absolutely have to have that central body of knowledge. I'm not going to talk too much about general problem solving, simply because there isn't too much about general problem solving in the world of AI. And you hear a lot about, if you read about AGI, where the G is general, then, and you're looking for examples and you don't find any, well, that's pretty much the truth of it. There is not much general intelligence, either in artificial intelligence or in human intelligence. Very little of our knowledge transfers over from one field to another. So what did we do in AI? What we did was a large number of specialty systems called expert systems, where the knowledge was honed to be the knowledge of expertise in a particular field. And all of those, and thousands of those were built. That's the first wave of artificial intelligence. Those are sometimes called rule-based systems, although other techniques were used other than rules. And they were not very deep, because the knowledge was so powerful that it pruned that vast amount of search that I was talking about. Finally, these are the systems I'm going to talk about today, these deep search systems that have weak knowledge but search a great deal for solutions, and indeed some novel solutions. I just want to show you the we hear a lot these days about deep learning influencing these recognition decisions over here. I call this deep search systems deep thinking, as opposed to deep learning. The fast and slow is very interesting. Doesn't that remind you of the title of Daniel Kahneman's recent book, Thinking Fast and Slow? It's exactly the distinction he was making. Our perceptual decisions are about 1/10 of a second, and we can't explain them. But our problem-solving, planning, abstraction can take hours, can take minutes or hours or days or months as we work deeply into a problem. Obviously, different kinds of processes. Okay, now we're getting into this search space idea. For any problem that we would regard as interesting and not trivial, the search spaces are very large. So, for example, let's just take games for the moment. If you were to play checkers with somebody, then you are wandering around in a space of possible checker games of 10 to the 34th power. Checkers doesn't seem that complicated, right? 10 to the 34th power. You'll see when I get to chess in a moment, in a few minutes, that it's the chess moves seem pretty restricted, an 8x8 board and just rigidly delimited pieces that can't move very much. 10 to the 100th possible chess games. I'll tell you more about that later. So in order to deal with these astronomical searches, you can't use brute force computation. No matter how many computers Google has, you can't apply them to a problem that's 10 to the 100th big. So you use what are called heuristics. Otherwise, the mathematician George Polya, who popularized the term, called it the art of good guessing. That's based on knowledge of the world, to make these computations tractable. And So that's a search space. Now here's another way to say it. I use the word combinatorial space. It's an exponential tree, all possible paths from an initial state to a result. And the metaphor for a creative act in a combinatorial space, a creative act, the metaphor is you're looking not just for a needle in a gigantic haystack, you're looking for a golden one in that gigantic search space. So it's not ordinary problem solving, it's golden problem solving. So let's take an example of the very first. This is amazing that at the beginning of AI, this is the first program, this one here, the logic theory program, the first program in AI that was ever done. And it was presented at the Dartmouth conference in 1956. It was the only running program in 1956. It was done by Herbert Simon and Alan Newell. Let me quote from the correspondence that Simon had with Bertrand Russell, because the logic theorist was proving theorems in chapter 2 of Whitehead and Russell's Principia Mathematica. And it proved all the theorems in chapter 2. And it proved one particular theorem, well, to quote Herb Simon, but in one case, that is the logic LT program, created a beautifully simple proof to replace a far more complex one in the book. And Russell replies in a letter to Simon, I am quite willing to believe that everything in deductive logic can be done by a machine. And I didn't quote the other part of it. And why did Whitehead and I waste our time? But this is so astonishing for the very first program. It was running on a machine called Johnniac. Here's the Johnniac. This was preserved originally in the LA County Museum. Now it's in the Computer History Museum. But the Johnniac was only 40,000 operations a second, and its memory was only 20,000 bytes. Compare that to the 500 billion bytes on the disk in your laptop, or the several billion operations per second in your iPhone, or in the cloud, where you actually in the cloud you have trillions of operations per second in one of these gigantic Google or Microsoft clouds. So what can we do if we had enormous amounts of computation? Well, let me do an intermediate step here, which so I can explain things a little more clearly. Let's just take one problem that the AI community was obsessed with for a long time, and that's beating the world's chess champion. It happened finally after much thrashing around and much prediction. It finally happened in 1997. It happened with deep search. The computer was called Deep Blue. The computer and its program was called Deep Blue. It was playing Garry Kasparov, who was the world champion at the time, but also most people regarded him as the best chess player ever. And as I mentioned, I said 10 to the 100th before. I was wrong. It's 10 to the 120th pass in a chess space, 10 to the 120th pass. Now, grandmasters like Kasparov, they only look in a move, they only look at a few hundred, 10 to the 2, not 10 to the 120th. But they have, by good pattern recognition from playing a lot of games in the past and knowing all the games that were played in tournament play, they have some wonderful pattern recognition. They have patterns that they recognize in the chess scene that allows them to manipulate large amounts of the chessboard in only a few hundred paths. If you don't have that kind of knowledge, then you have to search deeply. Not, of course, not by brute force, because you'd never get through 10 to the 120th. Well, Deep Blue searched for 200 to 300 million paths in its play. In the game that where Deep Blue beat Kasparov and gained an edge in the match. It looked at 280 million avenues in the search space. Now, for perspective on that, that's 2 times 10 to the 8th, or close to 3 times 10 to the 8th. That's nothing compared to 10 to the 120th. And yet, Deep Blue found a move which was spectacular and beat Kasparov. Actually, there were 2 brilliant moves in 2 different games of the tournament. So, is it creative? And let me give you, remember, this is evidence-based. We're going to decide whether it's creative looking at the evidence. How about the, what do the experts think? This is the guy who's the editor of Chess-Based magazine that every chess player reads. And he also served on Kasparov's analysis team. Here's, you can read what he says in his Chess-Based magazine. Round 2, Deep Blue must contain some highly sophisticated positional instructions that have never before been seen in a chess program. And then he says, or it calculated, this is his italics, or it calculated the variations to depths that defy imagination. Completely wrong. It was not depths that defy imagination. It was something of the order of 10, 11, 12 deep in a full chess space is about 50 deep, and Deep Blue was only looking at the first 10 or so. So it wasn't anything that defies the imagination. But just when everybody at last seemed to agree that Kasparov was actually winning, Deep Blue pulled out a most amazing defense, forcing Gary's king into a perpetual. Those who play chess know what a perpetual is. It's you can't get out of it. The maneuver left the entire auditorium gasping. Now, who's in that auditorium? They only let, in that game, they only let, well, there were a few people who were not masters and grandmasters in chess, but almost everyone was masters and grandmasters in chess watching that. And the sense of awe spread through the room as the computer made that spectacular move. Okay, now what did Kasparov think? So, I'm quoting from Wikipedia. Kasparov said he sometimes saw deep intelligence and creativity in the machine's moves. Now, what does he mean by that? Deep intelligence and creativity. Meaning, he was talking about finding that golden needle. Deep Blue found that golden needle in this enormous haystack called chess moves. This was a spectacular move, never before seen in the history of chess. And of course, chess has been played for centuries, maybe millennia. That move was never before seen, and it took the analysis team a long time to figure out why that move was so brilliant. Now, the computer that did that was much faster than Joniak, but it was approximately 11 billion floating point operations per second. It was, for its time, it was a mini supercomputer, 1998, actually 1997. So let's go on to the next game. I told you that there was another one, and that's the game of Go. Now, those of you who are game fans will say, but Go is really, really, really harder than chess. In fact, nobody thought a computer program would be able to do this now. That people's predictions ranged from like 2025 to 2050. But a program out of a company called DeepMind that was bought by Google, it put together the same kind of program I've been talking about for chess, except it added two kinds of machine learning, a pattern recognizer to get some of that pattern knowledge that I was talking about before, and knowledge to tune up the evaluation function for, when you can't search all the way down through the space, you have to evaluate how good it is where you are. And so they used the machine learning. They played large numbers of book games, and also the machine playing by learning thousands of book games and millions of games against itself. The size of the Go space is not 10 to the 120th. The best estimate that I could find in the literature is that it's 10 to the 800th. Did AlphaGo, all of this, and they needed an enormous amount of computer time to do this. And undoubtedly, they got it from Google because Google owns this company, DeepMind. So I'm guessing that Google provided either hundreds of thousands or millions of processors to do this. Now, let's look at what the experts said. What happened was that AlphaGo beat, maybe it'll turn up later, but AlphaGo beat 2 world champions at Go. And I say 2 world champions. How could that be? Because the Chinese claim that the world's champion is a Chinese, and the Koreans claim that the world's Go champion is a Korean. And AlphaGo beat them both. So let's look at some of the quotes. This is from the European champion. You can read them for yourself. I've never seen a human play this move. So beautiful, beautiful. AlphaGo played some quite surprising and beautiful moves. That's the president of DeepMind is summarizing what he heard. And then Wired magazine summarized the move was completely unexpected in that, a particular move that he's talking about, completely unexpected in that particular place at that particular time. A surprise all the more remarkable when you consider that people have been playing Go for more than 2,500 years. The commentators couldn't even begin to evaluate the merits of the move. It totally puzzled them. It's one of the things, that move was one of the things you teach novices never to do. And AlphaGo just went and did it and played beautifully in a totally surprising and awe-inspiring way. And again, evidence-based, that's creative. These are all comments of awe and surprise. It's extremely novel, and it's never before been seen, even though the game has been played in Asia, mostly, for 2,500 years. Okay, so here's the message. It's a joke. You know this joke. 2 campers are hiking. Suddenly they see a bear in the distance running toward them. They turn and start running away. But then one of them stops, takes some running shoes from his bag, and starts putting them on in place of his hiking boots. "What are you doing?" said the other man. Don't you think with those on you can run faster? Do you think that with those on you can run faster than the bear? And he says, "I don't have to run faster than the bear. I just have to run faster than you." That's the same thing with search. I don't have to search to the bottom of the search space. I don't have to search 10 to the 120th things or 10 to the 800 things. I just have to search deeper than you, and I will find that golden needle in the haystack that you couldn't find. Because you're a human and you can't systematically enumerate and search all those possibilities, even given the heuristic knowledge that you have about chess. So even if you're a world champion, you can't do it. I can search deeper than you is the main message. Okay, now let's, in the few minutes that I have left, I want to talk about cooperative intelligence, which is the place where I think AI is going. You see, Patty, I did say something about the future. Cooperative intelligence. Humans and programs like you've seen cooperating with each other, where the humans do what humans do best, the programs do what programs do best, and working collaboratively, they produce a result that is better than either of them could do themselves. Or even, well, when you think of acceptance, if you think of medicine, there's no way that these things are going to be accepted in medicine except as collaborative agents. I mean, doctors won't stand for it. So the most creative acts will likely come from these human-computer teams. And I have enough time to show you a couple examples. So here's one, this is roughly 1983, something like that. It involved a Stanford professor, former student in my lab, Douglas Lennett, and his program Eurisco, and a network of early workstations. The things that were working at Xerox Palo Alto Research Center that Steve Jobs noticed, and from that he got the idea of a Macintosh. You remember that old story, which is a true story. So Lennett is a game freak. In particular, he was working on, this is the company that produces these games. This game was called Trillion Credit Squadron. It's a war game. And it has a huge search space. In this game, it's not a board game. It's a game of books full of rules about how you acquire naval equipment and how much it will cost and what the rules of engagement are and who gets to shoot at whom, and just thousands of rules that you have to play through. So it's an enormous search space. The player builds a navy with his trillion credits. The objective is to defeat all other navies encountered in a national championship tournament, which in that year happened to be held nearby Stanford in San Mateo, California. So this is the way it would go. Lennett was an assistant professor at Stanford. He got Xerox to give him the use of all these workstations at night when on the original Ethernet. The invention of the Ethernet was done there. The original Ethernet had all of these computers. Lennett would start it up, and then in the morning on his way into work at Stanford, he'd stop by Xerox Palo Alto Research Center and look at the results that the search program had delivered. He had the search program deliver about 100 results every morning, and he would look at those and he'd choose from those with his whatever human knowledge he had that he hadn't articulated. He would choose what he thought were the few best, 3, 4, 5 best for further search, and prune all the rest of it away. Then he would go into campus, and then he'd come back at night, then in the morning he'd go in again and do the same thing every day for 3 to 4 months. And eventually, Lennett and Eurisco, they repeat again and again, the search, evaluate, prune, search, evaluate, prune. Shares the intermediate results with Lennett with guidance for further search. Now, what's the result? The result is that AI people are calling this, incidentally, this pair of human and machine, they're calling a centaur. So this particular centaur of Lennett and Eurisco discovers a remarkable winning niche in the game. It's a brilliant move. It's bizarre, totally bizarre. But somewhere in that gigantic space was this incredible move. And Lennett takes this move to the World Championship and sits down in front of the first other player. And the other player looks at the board, looks at the game, says, "Oh, I see what you're doing. I resign." And then he goes to the next table and does it with the next guy. Oh, yeah, okay, I see what you're doing. I resign. And Lennett wins the tournament. And of course, the tournament, the guys who, people who run the tournament were appalled by this. So they radically changed the game for the next year for the tournament. And Lennet and Eurisko did it again the next year. And incidentally, the move was spend all of your credits for that read dollars, spend all of your dollars on PT boats, because there was some specialized rules about PT boats that allow them to pop out, fire a gun, and pop back into safety. And so you could pop out your PT boats all over the other guy's Navy and shoot them all down and pop back in complete safety. So Eurisko won, Lennet and Eurisko won the second one, and then they were banned from further play. I asked Lennet, how much of the intelligence in here was you, and how much of the intelligence in this partnership, how much was you and how much was Eurisko? And he said he thought it was about 60% Lennet, 40% Eurisko. So that's the example of human-machine collaboration. Now I'm going to shift gears into a space where most people who come into a lecture hall to hear about computers and creativity, creativity first brings to mind creativity in art, particularly visual art, or creativity in music, a la Mozart or Beethoven. Not creativity in science or creativity in games or any of the other kinds of creativity. But people think of creativity in the arts. So let me tell you this other story. Okay, Harold Cohen. He's has been a well-known artist in the 1960s in modern abstraction, gets disillusioned with the community of abstract painters in Britain because he felt they were much too anti-intellectual, and accepts a job at the University of California, San Diego, when they were just starting up their campus. They had an art department. And he had read Newell and Simon's work on, and he had read my work on expert systems. And he thought, if ways of thinking by various kinds of experts can be captured in a computer program, then why can't I, Harold Cohen, capture my own way of thinking about art in a computer program? And so he began this process. I found out about this by being called upon to evaluate a proposal of his for, anyway, doesn't matter. I invited him up to Stanford he stayed for a couple of years on sabbatical and learned all the techniques. And so this was 1973 through 1975. Then he went back to UC San Diego. And up until the year that he died, 2016, he was continually working on this program of writing out remember I told you about rule-based systems? Writing out the rules of Harold Cohen thinking about his art, what he's putting down on the image, and how it relates to what comes next in the image. He learned all that computer language stuff. He also built robotic machines for painting, which you can see on exhibit at the Computer History Museum. Here's the collaboration. Aaron, this program, the expert system, runs and runs and runs and runs. It will always be generating a next new image, even on display in museums. There will be some images that Harold Cohen has selected, but there'll also be a computer projecting a constant flow of brand new images. Well, in the morning, Harold would get up and have his coffee, and he would look at all the images that had been generated, like Lennet did, all the images that had been generated overnight, and he would select a very few of them for further study, either 0 or maybe 1 or 2, which were exceptionally good. And then he would make a small printing of it because this paper he's using is very expensive. And then he would let that sit in his art studio for a while until he got really used to those. And every once in a while, he would say, okay, that's the one. And he'd make a big one of it, and that would be for a museum show or for a dealer. And there's one of Harold's images. This is one of the last, of course, this is actually a very large image, but it's reduced in scale for this slide. This is one of the last that Harold did in which Aaron had representational knowledge, that is, knowledge about things in the world. After this, Harold got rid of all that knowledge and just went back to abstract art, which you can see if you do Google under images and just say Harold Cohen, you'll see all of those. Well, you see a lot of Harold Cohens. Okay, so the question is, what does the art world think of this? Well, oh yeah, I wanted to tell you a little bit about every artistic element of the image is involved in the search. That is, the lines that are put on the image, the spacings between the lines, around the lines, the colors that are in the image. Harold Cohen is well known in the art world as a major colorist. And the search that I was telling you about, the combinatorial search using 15,000 rules, huge search space, every single one of those interacts with the image because you're not creating something out of the blue. You're creating something in the context of what's already down on the paper as the image. So do curators view this as creative? And the answer is yes. There have been many exhibitions in museums, international museums, and art galleries around the world. And I just happened to stumble in on one a year ago at the Victoria and Albert Museum in London. I didn't quite know how impressive that was, so I found this quote from the director of collections at the Computer History Museum, Karen, and she said, the V&A is the world's leading museum of art and design. The V&A is the gold standard by which other museums measure their own successes. So here we have a super expert, the V&A curators. And this is this is what they wrote about. I took this photo of the introduction to the Cohen exhibit at the V&A, but I'll just quote this last thing here. It says, through Aaron, Cohen has engaged the task of imbuing software with the creative instincts of a human artist, raising important questions about the nature of art, creativity, and originality. Remember, this is a human-computer interaction between Harold Cohen and what he knows about his art and the computer actually generating this images in this enormous space. So finally, let's talk about the future. Kitano, Dr. Kitano, he's president of Sony Computer Science Laboratories in Tokyo. It's one of Japan's leading AI scientists, one of the world's leading AI scientists, gave an invited lecture in July at the big AI conference, international conference, Ichikai. And his invited talk was called Creating the Engine for Scientific Discovery, Nobel Turing Challenge as a Grand Challenge Project in AI and Systems Biology. And he challenges AI within 50 years to make major scientific discoveries, some of which will be worth a Nobel Prize. In my view, what's going to happen is it will be a collaboration between a super smart human and one of these programs that will do something worthy of a Nobel Prize within the next 50 years. I also make the prediction that the Nobel Prize Committee will not award half the award to the computer. So, using enormous combinatorial or textual searches. I didn't have time in this talk to go over the textual searching, which is really playing a big role now in these attempts to do discovery in science. For example, reading 300 million abstracts and getting ideas for new possibilities in thermoelectric materials. That was one of the projects. With an expert human partner, systems of collaborative intelligence will find superb creative acts that mankind unassisted did not or could not think of. That is the end of my talk on art and of AI and creativity.
I'm sure there are questions, and Dr. Feigenbaum will answer them creatively. I have just a few, a little ceremonial entertainment for you here. I do also want to point out, as you've seen on every slide, that this lecture is the joint effort of the National Library of Medicine, of the Friends of the National Library of Medicine, and of the American Medical Informatics Association. And I would like to recognize that there are two officers of the Friends here today, and so welcome to the President and the Vice President, respectively, Barbara Redmond and Andrew Ballas, both of who are here today. Welcome here. Glad to have you here, partners, and we'll see you again next year. Now, every year, since the beginning of this, we have honored our speaker with something to remember us by, and to present the ceremonial bowl that's become sort of a tradition for these lectures here today. It's a very deep pleasure for me to introduce to you Mrs. Mary Lindbergh, who will present the ceremonial bowl to Dr. Feigenbaum. Mary?
On behalf of the National Library of Medicine, the Friends of the National Library of Medicine, and the American Medical Informatics Association, I'd like to present this award to you. It is the Donald A.B. Lindbergh and Donald West King 2019 Distinguished Lecture Award in Medical Informatics and Pathobiology. Both Dons would have loved your talk and supported your work. Thank you.
This ball is so big that I'm going to put a haystack in it with a golden needle.
Yeah, as a special token of our affection, Dr. Feigenbaum doesn't have to carry it or bring it with him. We will ship it to him. And now we open the floor to questions. Ed?
It's just like a Japanese audience. I got one.
Milt?
Yes. Would you press your microphone, please, so everybody can hear it?
Yeah, I had a question. And you didn't mention anything about deep learning, although I'm sure you've been, so what's your thoughts on that, and how far can that go? That's artificial intelligence, I think. Do you have any comments about deep learning and neural networks?
The other talk that I told Don Lindbergh I could give was a talk entitled AI is a lot less than and a lot more than you think. I showed you the lot more than you think. I didn't talk about the AI being a lot less than you think. there's a super hype going around about the value of deep learning, neural networks, what they can do. They're as narrow as expert systems. They're in narrow domains. You step outside the domain, they don't know what they're doing. So that's okay, as long as you stick to the domain. They do a pretty good recognition job, but you need typically 100,000 labeled instances in order to get the pattern recognized statistically. Sometimes you can get by with maybe 10,000, sometimes you need 1 million instances. And the world is just full of instances of things. So how can you get that many? Like, if you're going to use this pattern recognition and deep learning to be the thought engine for self-driving cars, how many different situations can the world get itself into when you're driving through the world? It's crazy, right? It's 10 to the 120th or 10 to the 800th, and you can't get data on all of those you can't operate as if you were just seeing things as opposed to thinking about things. Now, the thinking about things, unfortunately, is what Hahnemann calls thinking slow. When you think about something, it takes you seconds or minutes, but let's say seconds. Well, a car traveling, what is it? If it travels 100 feet at 60 miles an hour in a second or something like that. Anyway, you don't have a lot of time. So you put up with as good as you can do. But I think that when Patty talked about the third wave, what she's saying is that there will be a disillusionment after the hype falls off on this second wave, just as there was a disillusionment with expert systems after the first wave. Oh, incidentally, based on some work on some project that I'm involved with, the amount of computer time that it takes to do those neural network jobs is phenomenal. You really have to have a big computer or have access to a big computer to do that work. So it's great for Google or DeepMind, owned by Google, and Facebook and so on, Microsoft. But for university people in labs, where are they going to get that kind of computing? Well, maybe national supercomputer centers that Don Lindbergh helped to set up in the 90s.
Thank you.
I have a question for you, Ed. You've spoken a lot about AI as it actually is, as it was, and it's likely to be. I think most people in this audience, and probably all over the world, do have some familiarity with AI as it's known in movies, for example, The Terminator. What do you think about general intelligence, something that actually simulates the intelligence of a human being? How near is that prospect, or is it possible at all?
When I showed that spectrum of AI, the straight line that went across, I commented on that little part called general problem solving. And I said that there are very few results there. In fact, only one I can really, well, two I can think of, but they never really produced any significant applications because there isn't much general intelligence. We don't have much general intelligence. We have enough to get us up in the morning and maybe get us down to work on some old habitual route that we follow. But if we had to think about it, in fact, we don't even think about it. We turn on our GPS, and it takes us there. Most knowledge about the world that is needed for problem solving doesn't generalize. You cannot, for example, there's a very good neural network program that is able to detect whether a dermatological lesion is likely to be cancerous or not. What kind of a lesion it is, anyway. And that was published in Nature. But you can't take that kind of knowledge, which is gained by dermatologists labeling an enormous number of images of those lesions. You can't take that and apply it to the inference of what's this patient's problem given this hip MRI. That's why the world is segmented into little portions of expertise. I don't know how to repair my car. I know how to drive my car. So I take it to an expert, a mechanic. So I used to say that there was no generality in intelligence, and Al Newell then accused me of, he called me the big switch guy, which is that thinking is turning the switch to whatever expertise you needed, and that would solve the problem. Because he believed that there was some general problem-solving capability. I thought we had put that to rest with Dendral and some of the other expert systems, but it keeps living, and it just got a $1 billion grant from Microsoft to a consortium called OpenAI to research the problem of AGI, Automated General Intelligence.
Well, we won't quote you, but then all these people who are prophesying doom in the next 20 or 30 years because the robots are going to take over, they're smoking something?
So one has to be very careful about, the problem is the answers to your question are, in every 1,000 answers, 999 of them are off-the-cuff answers for which there's no evidence and no deep thinking. And one of them is somebody thinking deeply about that. And you have to partition the future into different aspects of the future and ask specifically, what is AI going to do to this and that and that and that? When you think of AI doing everything at once, like a Terminator or Ex Machina, that woman in Ex Machina, don't believe all of that. But people like Eric Bjorlenson from MIT and his colleagues there look very carefully at the nature of work in societies, in modern societies, and exactly where are the AI capabilities that are coming up. Where in that world of work are those capabilities going to be applied? And therefore, people will either have to learn to collaborate with the AI, or their jobs will change, or they won't have a job. But that's a specific thing having to do with the effect on work. And similarly, you would have to take that same stance with regard to medicine or physics or anything else. You look at what the capabilities are and then ask what the future of AI in that area might be. So the good news is there are some people, including a member of the NLM Board of Regents, Eric Horvitz, who understand that extremely well. And Eric and his wife endowed a 100-year AI project at Stanford. It's a rolling 5-year assessment of what is the technology doing, what did we learn, what's coming up based on what we learned, and what will be the applications of that. And every 5 years, there's a report. There's a 2016 report, for example. All you have to do is look up ai100.stanford.edu. Barbara Gross was in charge of, from Harvard, was in charge of the first committee to produce a rolling report, and then there's another one going on right now, another one going on. The principal investigator is, of this project is one of our Stanford MD PhDs, Russ Altman. That's the way to approach your question, is to look at it on a rolling basis as the capabilities change over time. And make sober assessments. That is, the people on this committee, that is every choice of a 5-year committee to do this report, they have to be the very highest level people, not the journalists and others who write about AI.
We don't mention journalists in this study, but I see no hands up, so I'm going to add one last question. There's no difference in your mind then between the creativity that might arise from a sufficiently programmed machine who would win the Nobel Prize and the creativity of a human? The criticism has been made that the machines actually are imitative in some way. I'm just quoting what people say, and that it's not creativity in the sense we usually attribute to the people you've been quoting, Mozart or some of these others. But it sounded to me as if you think there's no difference, and there's no reason why a machine would not in fact be totally equivalent given a few more years. Is that true?
Yes, that's correct. And I specifically wanted to start this talk off with Turing's lesson that we should look at the behavior of the entity and not make any speculations about whether Mozart was too great to be imitated, or just look at what it does. Does it inspire awe? Does it come up with solutions that are novel, new to mankind? And so on, what I gave you in the talk. If that's the behavior, then that behavior is creative. That act of Deep Blue in finding that incredible move that beat Kasparov, or in this amazing style of playing that AlphaGo did to win those championships, that's absolutely creative. It wasn't imitating anything. It was searching in that vast space, looking for that golden needle.
Well, there you have it. That's the take-home. Behave like Mozart, and you've got a great future ahead. I see no other questions, so I invite all of you to step out into the lobby here and have a Sprite and some cookies on us. And let's thank Dr. Feigenbaum once again.
That was pretty wonderful.